Okay, here's what I want from you. No friction. I just want to see if you can do this. There are a couple of forces acting on the box. I am applying a force to push the box up the ramp. The box moves up the ramp at constant velocity. Okay? So there's an applied force on the box that allows the box to slide up the ramp at a constant velocity, no friction. I would like you to calculate the work done by each force on the box. Okay? I want you to calculate the work done by each force on the box. Are any of the forces that are acting on the box changing? All right, so they're all constant forces. That's an important question, and one that we're going to actually take issue with today because it determines which way we can kind of go when it comes to calculating work. I mean, we can use the top one anytime. That's a more general one, but if we know it's a constant force, so we can just drop down and multiply the size of the force times the displacement and take the direction into account. It should not be lost on you, and this part has been a problem for me today, that this is just mg sine theta. Somebody asked me, I don't know when to use sine or cosine earlier today. I'm using sine here specifically because I know that the weight is broken up into two components, and one of those components is down the ramp. I have to apply a force that's at least equivalent to that, which I believe works out to be 34.2 newtons. That's how much force I have to apply for the box to slide up the ramp at a constant velocity. Any question about where that came from? Yeah. I don't think it's much to point out that there's these three forces, this pushing force, normal force, and the weight. We've seen this a lot at this point. So if I want to calculate the work by that force, this is the work by my pushing force. It's going to be 34.2 newtons. That's the size of the force. The displacement is 10 meters. And here's where a lot of you have it wrong. Cosine is 0 degrees. This is the angle between the pushing force and the displacement. The pushing force is up the ramp. The displacement is up the ramp. Right? This sine theta had to do with the ramp stuff and balance of forces and choosing a coordinate system. But this angle is specifically about the calculation of work and the relationship between the direction of the force and the direction of the displacement. All right, which force do you want to deal with next? We've done one. What's another force acting on the box? Normal force is another force acting on the box. I think we could figure out the size of the normal force if we wanted to, but I don't think it's necessary. But the normal force has to be mg cosine theta. It has to be, right? Because it has to be balancing the portion of the weight that is into the ramp. But I don't think I even need that. What's the angle between the normal force and the displacement? Looking closely at my picture, normal force has to be this way. Displacement has to be this way. That's 90 degrees. Under this circumstance, the normal force does no work because it has no component in the direction of motion. So here we get 342 joules, but here we have 0 joules. What's the last force? Work done by gravity, yeah. Gravitational force is 100 newtons, right? 10 times 10, mg. Displacement's 10 meters. What is the angle between the displacement and the weight? the weight is this way, and the displacement is, hopefully we all know, the displacement is this way. Right, that's the displacement's direction. We're looking for this angle here. 110 degrees. You guys see why it's 110? All right, so cosine of 110 degrees, which, by no surprise, is negative 342 joules. Has to be, doesn't it? Does the object's velocity ever change? Are we all paying attention? Does the object's velocity ever change? No, we say in the beginning that it moves at constant velocity. Therefore, the net work had to be equal to 0. If the net work wasn't equal to 0, there would have been a change in the kinetic energy of the box, and it would have had a change in velocity. Again, I guess it's been a long time since the 16th. So here, let's have you try another one, and I want to help Les, so I'll be calling somebody out. I'll try and make this as straightforward as possible, but still staying within our realm here. How about I have just a box that's being pulled on by some upward tension, say 100 newtons of tension. You know, the 8.5 kilogram box. Again, I want the work done by all the forces acting on the box. Let's say the box was displaced 5 meters. And if it started from rest, how fast is it going now? Now, I hate to even ask this question, but is it clear what the direction of the displacement is? These are the forces acting on the box. I hope so. All right, I'll give it. So Noah, what do you got? Can you help me out with any of this? All right, help me out.
So you gave us the force of tension, so that's 100 times the displacement of 5 times cosine 0. So just moving and looking at the displacement, you get 500 joules of energy. And then for the work of gravity, you get the 85 newtons times the 5 displacement, and then cosine 180 to get a negative. So it's the opposite way. So you get negative.
All right. I think you did a bang-up job. Any questions about that? Network done, 75 joules. Now, is it lost on anybody that the net force would have been 100 newtons minus 85 newtons? Right, because I have 100 newtons upwards and 85 newtons downwards. And that would have been a net force of 15 newtons. I'm saying that because if it was net force times displacement, we still would have gotten 75 joules, right? This all has to work the same. In the same way that we could have set the net force equal to ma to get the acceleration and used acceleration to figure out how fast the box is going, but I would have preferred you not do it that way. I was hoping, and I really do believe some of you did this way, you'd have gotten your 75 joules and realized that had to be the change in kinetic energy of the box. And if the box started from rest, that just meant that 75 equaled 1/2 mv squared. All right, minus 0 since it started from rest. you're going to start to have options on how you can handle problems. Consider your options, but also consider that you have to make choices about what's going to be the most efficient way to get to an answer. This can't tell you how long it takes. The only way to figure out how long it takes would have been to find that acceleration and then use a motion equation, because we don't have another alternative here. But look for efficiencies. You're going to have to. Of Hooke's law, F equals minus kx. This is for what's known as a linear spring. And it's linear because this function is linear. It's a direct proportion. I want to be clear, there are lots of different kinds of springs in nature that are not linear springs, that would have some other function here. But the thing about Hooke's law and any function dealing with a spring is going to be that you get force from a spring, and that force is going to be dependent on the displacement. The more you push on a spring, the more it might push back. Different kinds of springs obey different kinds of formulas. But a linear spring will be a direct proportion. If you double the displacement, it requires twice as much force to do so. In fact, the force isn't constant as you compress the spring. So if we say that right now the spring is in its relaxed state, then it requires no force for the box to stay there at the edge of the spring. But if I want to compress the spring some distance, no matter what distance I wish to compress the spring, that doesn't look very compressed, let's make it look compressed. There. No matter what distance I wish to compress the spring, when I move the box, whatever distance that is, our delta x here, it takes an ever-increasing force to do so. So by the time I've compressed the spring, even if the box is in equilibrium, it would require that I be pushing this way on the box, and the spring will be pushing back. Does that make sense? But that force increases if I want to compress the spring more. Now, this would be true if I pulled out on the spring as well. It doesn't matter whether we're talking about compressing a spring or extending a spring. The force still works the same. Your lab was about extending the spring, not compressing the spring. What I want to impress upon you is we can calculate the work done to compress a spring. And there's good reason to do so. I want you to think this kind of through a little bit. Anybody ever have one of those cars that you pull it back and when you let it go, it kind of rolls forwards? Or played like a pinball game where the ball is released because you pulled back on a plunger and then shot the ball onto the playing field? These all sound like things that you're familiar with. When you pulled back, you did work on the spring and put energy into the spring. When you released the plunger or when you released the car, the work you did on that spring stayed in the spring. And the spring was then able to deliver that energy back, in this case to the ball or to the car or to the box. This reciprocation of energy is something we want to develop. And so I'm going to start with talking about a spring, and then we're going to talk about springs and gravity and other things that can do this. So we'll start with the spring today. In order to understand this conversation, though, there are some things about it that I need you to be prepared for. We're going to press on the spring this way. This is us. This is our force, our pushing force on the box. The spring, of course, is applying a force in the opposite direction. The spring is pushing this way. See the force from the spring. Hooke's law is about the spring, remember. So the negative sign in Hooke's law is to tell you that if I push the spring to the right, the spring pushes back to the left. That's what that negative sign is about. We're just going to focus on the size of that force, because that's what we're really interested in, because we're going to try and calculate the work done. There are two forces here, right? There's my pushing force, and then there's the force from the spring. So let's start by talking about my pushing force. Now, I can't use this to calculate the work done. The force wasn't the same through the displacement. The force was getting greater and greater and greater. So every little bit that I moved the spring required an increase in the amount of force. The only way that I can calculate the work done is to change this from a simple product to an integral. Now, for those of you who haven't done calculus, you're going to have to learn some. And I've not made a secret of this. Most of the calculus that I want you to know, I will focus on second semester. I need you to follow along with this, though. The result of this is very important, and you'll have to know the result. How I get to the result, I want you to see. I want you to understand a little bit of it, okay? So we're going to start here. We're talking about our pushing force. So we still do the same things that we've done in the past, except that our integral really is supposed to tell us where we started and where we ended. So we're going to start with the spring relaxed, and we're going to end with the spring compressed some distance, capital X. I know that I have X's all over the place. This is just a reminder to us that where did we start with the spring and where do we end with the spring. The pushing force, how hard we have to push, is based on Hooke's law. So that's going to be Kx. This dx represents a small change in position. The d is still a delta, and it still has directional information. So I do have to evaluate the dot product and put an angle in here. And this angle has to represent the relationship between my pushing force and the displacement of the box, which I think we can probably all agree, if it's my pushing force, it was in the direction of the displacement, so that's going to be 0. Are we good so far? Now, all of that is fine until this point. Well, we now have to evaluate the integral. And for those of you who don't know much about this, I want to just give you some quick tips and stuff about this. The cosine would have to be moved over here to be inside where the dx is, because an integral actually has a format. And this kind of act like parentheses. They're not, but they kind of act that way, in that the part in the middle is called the integrand. It has to be all of the things that are being calculated. So technically, we'd move the cosine over. But this is cosine of 0, which is just 1. So I can kind of ignore that for now. It's just 1. But I'm not lying when I say that these things kind of act like parentheses. The only difference is that this dx tells you something very important, that the integrating variable is x. That's the important variable. Any other letter in there, we treat like a constant. So the k is just a number, just a constant. But the x is important. So we look for anything that has an x or a function with x in it. The x here is just a polynomial, right? This is x to the 1 power. So the parentheses that I have written here are telling me that I'm going to take this and find the antiderivative. That's what we're doing when we're taking an integral. Now, you've done this part before. X to the 1 power is just x to the 2 power divided by 2 when we find the antiderivative, because it's a polynomial. K doesn't go anywhere because it's just a constant. Nothing happens to it. Which means that our answer is 1/2 kx squared. But we have to evaluate it from 0 to capital X. We'll have to come back to